This video is of the graphic of the yeast nucleus. Um, this is a paper by the group at the University of Washington in Seattle. This is what you'd call a medium resolution structure, as compared to the paper in Science from the Broad Institute on the human nucleus, which had no data set associated with it. And what we see here is a structure of the 16 chromosomes of yeast at a resolution that you would consider to be, sort of like a 4 angstrom protein structure. 4 angstroms in proteins, you can see the general outlines of helices and sheets and so forth, but you can't really understand the atomic interaction of the individual atoms and charges and so forth in the structure. So this is very interesting because for the first time you see just how complex the nuclear structure of the yeast genome is. So I'll turn off each of these chromosomes in turn, and you see how it's getting simpler and simpler. Then we'll go back and look. So here's chromosome 1, and it has a particular shape, and it's a sort of unresolved shape. But here you see what this solution of the nuclear structure does. It shows you approximately what the shape of chromosome 2 is and approximately how close it is to chromosome 1. Here's chromosome 3. So you see that 3 and 2 are closer to each other, and so therefore you'd expect that there'd be much more interaction between those chromosomes. Here's chromosome 4, which is off by itself and has a complex structure all of its own. But it's sort of just squiggly. It doesn't have any real definition to it. Of course, the people who did the project would say, oh, no, it's quite highly resolved, but it isn't. And here you see the chromosome 6 is off by itself in this particular aspect, and that 7 is close to 4 here, and close to 6. No, that's 6, 5. Nope, that's 1. It must close to 1. Okay, so we're just playing with this here. And so then this is chromosome 7, and you see how it's beginning to pack in with the others that are present. It's interacting with a variety of chromosomes. And chromosome 8. So, of course, you can take any pair of these things and study just how close they are to each other. Not. Yeah, so these are, close in that one region. 4 and 8. Here, see, 8 and 3 are somewhat closer to each other. In any case, so I'll put all of them on here so you can see the structure building up. And here's number 9 coming in over there, and 10, and 11. And of course you can, as we did before, you can take them pairwise or triple-wise and play with the understanding. This is 12 coming in, 13, 14, 15, 16. So you can play with this forever you want. Now, the most stunning aspect of this nuclear structure, at least to my way of thinking, is this chromosome 12. When you see this thing here, again, the resolution is only medium, but this is the only case in yeast where there's a whole huge clump of chromosomal structure that's interacting quite strongly with itself. Now, if this sort of structure occurred in several different places in the nucleus of yeast, you'd say, oh, well, that's just the way that those things do happen. But it doesn't. And so chromosome 12 is the only one where there is this clump. And I mean, one of the things I've not done yet, and it's been a couple of years and I should have done it, is to determine the connectron structure of the yeast, which I've done in the past, and then overlay that determination onto this graphic. I just never got around to doing this. I'm sorry. But my sense is that this clump of structure would have a huge number of connectrons that are forming this dense clump of structure, and that this is an intrachromosomal clump. I mean, it may have external signals sent from other chromosomes to this thing. There could be some event on chromosome 8, for example, that helps to form this clump. But my sense is that this clump would be intrachromosomal rather than interchromosomal. In any case, this yeast nuclear structure, I mean, we've grown accustomed in the last couple of years to seeing receptors and great machines, the ribosome, polymerases, in atomic detail. And the nature of helices and sheets have been borne out from the very first structures, hemoglobin, myoglobin, all the way through to these receptors. But here, for the first time, we see nuclear structure, that is DNA structure. And to my way of thinking, this structure that you see here is more complex than any protein structure that I've seen. I mean, and this includes well, maybe the ribosome is as complex. I don't know. I'm certainly impressed with the complexity of this structure, and this representation in Mage King is really very, very beautiful and very powerful, and really helps you to understand something about the nucleus. I mean, but it's clearly still a medium, at very best, a medium resolution structure. And we would hope in time that this structure will be resolved more fully, and we'll learn more about how the pieces interact, why they interact with each other. My sense is that connectrons really will have a role in the nuclear organization. I mean, I've been thinking about this for a decade now, and but it's been a decade, since the genome of the yeast was sequenced, until we finally have this medium resolution structure. And so these things take time, but this is a fact, a medium resolution set of facts, but it doesn't show why these structures are the way they are. And I think that's the important thing, to make the transition from the facts, to the why. And this is never, well, I wouldn't say never, because people do, with respect to protein structures, say, well, look, this is the mechanism of action of this particular protein. And so one would hope that in time there would be a description of why these pieces are interacting, and how they're interacting, and why, for example, this clump of structure here on chromosome 12 exists, and then what the meaning of that, if there is any meaning. So this is, again, a very powerful graphic, and I think you should play with it and think about the nature of a nuclear structure, and possibly the role of connectrons with respect to that.